Okay, just for now, we talk about the intrinsic semiconductor. So in principle, it's possible to create free carriers in intrinsic semiconductors, signal damper by thermal agitation, right? But because the band gap of semiconductor is much larger than that of the thermal energy, so that's the reason why the free carrier which we can create by using this thermal excitation actually is quite low. And of course, you may ask a question, if that's the case, why not we just reduce the band gap and use a semiconductor with a much smaller band gap? If that's the case, and then we should be able to create more free carriers. In principle, this is right. What I said is right. But if this is the case, this also means that the device is going to be very sensitive to temperature. So this means that you have to, in order to ensure certain stability, and then you have to use the device at a very low temperature. So this basically, so what does this mean? This means that it's not serve the purpose, right? So that's why we still need a semiconductor with a reasonably large band gap, and then we need to find another way to introduce free carriers. So this is basically called doping. Okay, the starting point for all the semiconductor manufacturing is always to grow this kind of large, very pure single crystal, right? And so, of course, we don't have so many companies who can do that. And then we only have a few suppliers who can manufacture or grow this kind of a large crystal with extremely high quality, right? So once we have this kind of pure semiconductor single crystal, then we can slice this into a very, very thin layers we call wafer, right? And then we can use that wafer as a starting material, and then we sometimes we call substrate, right? And then on top of this wafer, we can deposit many other layers, including the silicon as well. And in this case, so we can try to use a technique which is called doping, which we will talk about later, and to introduce a different level of impurities, also different types, into the pure silicon layer. And by doing so, and then we can fabricate many different type of devices. So this means that this kind of intrinsic semiconductor, although it's not good for carrier, not good for electric conduction, but we need this kind of material as a starting material to fabricate electronic devices. So the typical process would be like, so once you have the wafer, and then so what do you do that? So on top of this wafer, and then you can deposit, other type of materials, including the semiconductor, as what I just mentioned. And then so during this process, if you only deposit pure silicon on top of another pure silicon, of course, this will not be very interesting, and also it's not very useful. So what's useful is that you can deposit additional silicon layer on top of this wafer, but at the same time, you can selectively at a different position, you can introduce a different amount of impurities. So this is basically called doping. And also you can choose the impurity items such that in a certain area, you have dominantly have more electrons. So this kind of impurity is called donor. And then for that area, you may have more holes. So this is called p-type. And the impurity you use to introduce additional holes is called acceptor, right? So once you have this n-type and then p-type semiconductor, and then we can fabricate semiconductor devices, right? So what's shown here basically is a typical MOSFET, which is the single most important electronic devices for the entire IT industry. So you start from, for example, this n-type layer first. This basically is doped by donors, and so when you apply electric field to this layer, of course the electron will start to flow. So basically, this will give you electric conduction, right? And so you can selectively dope some regions, for example, here and here, into p-type. So, and in this case, you know that you have holes, you have many holes inside this p region, and also holes in this region, and then you have electrons in this region. And then what happens that at this junction, and then you have an energy barrier.
So this energy barrier will prevent hole to flow freely from here to here. And so basically, if you use this as a switch, so basically the switch is off. And in order to let hole flow from this region to this region, or vice versa, and then you need to remove this barrier. So this can be done very easily by using this kind of we call electrostatic gating effect, right? So there's a metal here, and you connect this one to apply, for example, a negative voltage, to this terminal respect to this body, and then you can attract holes into this region. So it causes some sort of conduction type of inversion, right? So once you have this is equivalent to say that you reduce this barrier, and then this holes will be able to flow from this side to this side if you apply electric field, basically to apply voltage between these two terminals, right? So this means that this switch will be on. So this MOSFET so basically is a very good switch, electronic switch, right? You can make it very, very small, and of course you can also use this one to amplify the signal. So this means that you can apply a signal here since a small change in this gate voltage will induce a large change in this channel current. So this means that you amplify the signal. Of course, you don't amplify the power because you draw the power from the power supply. You don't amplify the energy, right? So that you draw the power from the power supply, but you can see that the signal amplitude so basically is amplified. So you have the amplifier. Okay. So now in to this part, basically we need to understand how to introduce impurities into semiconductor to make the N-type and the P-type.
Okay, and to do this actually is very straightforward. It's not so difficult. So what happens is that, for example, if you look at pure silicon, so as I
already mentioned that in the perfect silicon crystal, and each silicon atom will contribute 4 valence electrons and to share with the nearest neighbor 4 silicon atoms. And then so this electron cloud will overlap with each other to form a covalent bond. And then this bond at a finite temperature, and this bond actually is quite strong. That's why at the finite temperature, there's only a very small possibility or probability for this electron to escape from this bonding and to become a free carrier, right? And so that basically is an intrinsic semiconductor. So now, suppose if we replace some of these silicon atoms by other type of atoms, which in the periodic table either next or right to this silicon atom, and then you know that so if you have, for example, silicon anyways group 4, so we have a group 3 element, for example, like a boron, and then of course boron we only have 3 valence electrons. So if thermodynamically it's possible for this boron to substitute some of the silicon atoms, and then so for example look at this one, and then of course so this boron atom will only have 3 valence electrons. So it can share this 3 valence electrons with the 3 of the 4 nearest neighbor atoms. And then the other one, so this means if you want to share this, basically you have 1 electron which is missing, all right? So if this means that you need to borrow 1 electron and to form something like borrow 1 electron to form this bond. So this means that you create a hole, right? Because when you create a hole, and then this hole actually is loosely bonded to this the nucleus of this impurity atom, the boron, right? And then of course at a finite temperature, since this bonding is much looser than this silicon bonding, and at a finite room temperature, so basically you can assume that so all these holes will just escape from this boron, so which you call ionization, right? So when this happens, and then you have of course here we want to look at a single boron atom, and then if you substitute many of the silicon atoms by boron, and then you'll create a lot of free holes, right? So this means that you don't need to rely on the intrinsic mechanism and just use this extrinsic mechanism, you can create a lot of holes. And so this kind of dopant is we call acceptor, right? So because it creates additional holes. And similarly, if you substitute this silicon atom by group 5 elements, for example, phosphorus. So in this case, because phosphorus has 5 valence electrons, right? So this means if it uses 4 of the valence electrons to form a bonding with the neighboring silicon atoms, and then it has an extra electron. So this extra electron will be loosely bonded to this nucleus. And then this electron at the room temperature can escape from the attractive force from this nucleus and then become free to move, right, inside silicon. So if you add more such kind of impurity atoms, and then you create a large amount of free electrons. So this kind of impurity called donor because it donates 1 extra electron, right? So now, why is it so easy for this extra electron to escape from this impurity atom if it's in the environment of a silicon? That's due to actually screening effect, which we'll talk about later. So what happens that if this phosphorus atom in vacuum, right, in isolated state, and then there's no screening, no very strong screening between this electron and the nucleus, right? Because basically the inside atom just can think this is in a vacuum. Okay? And however, if you put this one in the silicon, and then this electron will feel the dielectric constant, the screening effect due to the dielectric property of the silicon. And this dielectric constant actually is quite strong. So what does this mean? This means that this charge will induce some sort of a polarization, right, between this electron and this nucleus. So this polarization basically will screen out the electric field due to this nucleus partially, and then eventually this will become loosely bonded to this nucleus. So that's the reason why this can escape from the nucleus at room temperature. Okay.
So, so this again is called ionization. So of course, the degree of ionization is determined by both the temperature and also this so-called bonding energy, right? So, and in quantum mechanically, and we can actually estimate this ionization energy using a very simple
model that basically is a hydrogen atom model, which we discussed before. So we know that in quantum mechanics, and so in the hydrogen atom, you have 1 electron, which is orbiting the nucleus, right? And then this electron will take discrete orbitals, and at each different orbital, now you have a different energy. So in quantum mechanics, people already calculate this energy, which is given like this. You can see that you have so of course 2 and 4 these are just numerical constants, so just ignore it. Pi is a constant, and then you have this epsilon naught. So as I mentioned that because each electron inside this isolated vacuum, and so basically isolated atom, so basically experience some sort of vacuum as a medium, right, between this electron and nucleus. So that's why we want to have this for Coulomb interaction. We want to have this dielectric constant of the vacuum. Okay, and then so E of course is a electron charge, which is a constant, and the N is an integer. And then this A naught we already defined, when we talk about the hydrogen atom. So in quantum mechanics, we find the A naught basically is given by this. So again here, so we have a Planck constant, and then we have this vacuum dielectric constant for vacuum, and then this is the mass for electron, and then this is the electron charge. So this means that when you compare this with for example, the donor impurity atom in silicon, and they are very similar. So you can see that, so here, so phosphorus, so initially before you put this one into the silicon host matrix, so this atom basically is neutral, right? You have a equal number of positive charges in the nucleus, and then equal number of, electrons, right? So now, since part of the valence electrons, actually 4 of them will be used to form a bond, atomic bonding with neighboring silicon atoms, And then so this extra silicon will become a loosely bonded to this. And so, so in this case, you can see that effective positive charge of this phosphorus ion basically is just 1e. Why? Because this is the extra charge which you just take it out from this neutral atom. So that's why you have one electron here, and then this will be a positive charge will be also 1e. So this is very similar to the hydrogen atom case, right? So effectively just treated this one as a nucleus of hydrogen. Of course, this nucleus is much larger than hydrogen, but in terms of the number of charges you have, which is the same, right? And then this electron, you can treat this one as this electron inside the hydrogen atom. But the huge difference is that now, due to screening effect, and then this radius will become much larger than the atomic radius, right? Why? Because you have an epsilon naught here. So the epsilon naught, so for hydrogen atom is epsilon naught, but for silicon it's a epsilon. So it's a dielectric material constant for silicon. So typically it's much larger. It's about 11.7 epsilon naught, right? So if you have studied solid state physics before, you know that for dielectric materials, so the dielectric constant basically is written as a relative dielectric constant epsilon r and multiplied by epsilon naught. So epsilon naught is a dielectric constant for a vacuum, right? So basically this one. So for silicon, this epsilon r is 11.7. So it means that it's 11.7 times larger than the dielectric constant for vacuum. So this means that simply this will become 11.7 times larger, right? So this radius. And then of course, and you have an m naught. So in silicon, the effective mass for electron is smaller than the effective mass, than the mass for free electron. So this means that this will further increase this A naught. So eventually this radius become maybe much larger. So when this becomes much larger, of course, in between, you'll see a lot of silicon atoms, right? A lot of silicon atoms. So this silicon, again, has a dielectric constant of 11.7. So this will give you additional screening effect. So this screening effect will reduce this bonding strength. So that basically is this epsilon, right? This is due to screening effect, to take into account the screening effect, okay? So eventually you can see that, so this will, epsilon naught will increase by epsilon r, because this will be replaced by epsilon. And then this A naught will increase by another epsilon r, and then divided by a number which is smaller than 1 is due to this effective mass, right? So that's why eventually, as a first order approximation, this bonding energy can be written just like this, right? So this actually is called ionization energy of this impurity. So that basically is given by 11.6. So that basically this one. So minus means that it's a bonding state, right? This means in order to remove this electron, you need to supply this amount of energy. So that's why I call minus. And then it's reduced by epsilon r squared, right? So 1 comes from here and 1 comes from here. And then, and also another prefactor of effective mass, because the effective mass typically becomes smaller in semiconductor compared to free electron mass, right? So and then similarly, if this is boron and they have a hole, and the hole basically have a positive charge here, and they have a negative charge in this ion, and so although it's different from a hydrogen atom, but situation is similar if you just change the sign of the charge, right? So that's why you can still use the same model to calculate the ionization energy. In this case, it's given by this one. So you still have this epsilon r squared here, which is similar to this one. But of course, this will be whole effective mass instead of electron effective mass, right? And then 13.6 still here, okay? Now, and so actually people already find the ionization energy of different type of impurities in silicon. For example, so what's shown here, and then you see the silicon and the germanium, right? So for donors, for example, you have phosphorus and then arsenic. So especially for phosphorus, it's just about the 45 milli-electron volt, right? So these are called shadow donor. So typically in a band diagram, so for intrinsic semiconductor, remember band diagram, you only have valence band and the conduction band, that's it, right? So now for extrinsic semiconductor, and you have another energy level here. So this basically is called donor energy levels. Okay, so from this donor energy level to this conduction band edge, so this is called donor ionization energy, which is called ED. Okay, that's basically this one. For example, if you dope silicon by phosphorus, and then this will be 45 milli electron watt. 45 milli electron watt, because this is EV, right? And then if you dope this one by arsenic, and then it will be 50. Okay. Similarly, if you dope boron, and then you get the acceptor, of course, the acceptor energy will be here, which I have not shown here. And then from acceptor energy level to this valence band edge, so that will be ionization energy of acceptor, right? So for boron, is 0.045, basically it's 45 milli electron volt, same as this one. And then for aluminum, it's 60 milli electron volt, right? And then of course, germanium, and it'll be different. That's because that the effective mass is different. So remember, effective mass for germanium is smaller. The dielectric constant is also different. So that's why you can see the ionization energy in general, for example, for this both acceptor and donor, and then it will be smaller compared to silicon. All right, that's due to difference of effective mass and then dielectric constant. Okay, so this kind of shallow impurities are very useful, because later we know that we can use this one to introduce free carriers into either in the conduction band or valence band, right? But sometimes you can also have deep impurity levels. So these deep impurity levels in general are undesirable for semiconductor materials. So typically, for example, if you want to create more free carriers, or you want an electron host to move freely instead of tightly bonded to the impurity nucleus, and then you don't want this kind of deep impurities. So the deep impurity, typically the energy level will appear somewhere here, right? Much deeper, right? For them, for donor appear here, and then for acceptor appear here, right? Okay, and then for certain applications, the deep impurity energy level actually we don't want it, but for certain applications, actually sometimes we also want to have this kind of deeper impurity levels. And that because this kind of impurity level typically can, for example, can capture all the carriers, very quickly, or can make a recombination of the carriers at the excitation state very, very quickly. And this may be useful in certain applications, right? For example, if you want a very fast optical switch, and actually it's a product, okay? So what is, so basically you have something like this one. For example, you have a semiconductor. So this semiconductor has a lot of deep energy levels, which is not conducting, right? So this means that it's not very conductive, because you have all these deep energy levels. And so you put one electrode here, say for example, right? And then another electrode here, okay? So now if you apply a bias, electric bias to this one, and the current will not flow, because this base is almost insulating, right? And however, and if you shine a light, right, you shine a light, very strong, for example, laser beam or whatever, right, some of this one, and then so this laser beam will excite intrinsic carriers, and then suddenly this become a conductive, right? So now, so if you remove this, and then remove this. If you remove this laser, and then immediately, and of course, all these free carriers will try to recombine, right? If you don't have any deep energy levels, and what happens that this all this carrier will recombine relatively slowly. And however, if you have this kind of deep levels, and sometimes this recombination can be very, very fast. So when this happens, and then, for example, if you put your load here, so typically, so this is a load, any whatever device you have, we just call load. And then if you want to supply a very short electric pulse to this one, and this can be a very useful technique, because you can turn on the light on off very quickly. We're talking about say picosecond, that kind of time scale. And then, and if your carrier can also recombine at that kind of speed, in principle, you can create a pulse which is in the terahertz frequency range, and then directly apply to this device. So that's why sometimes it's very useful. And also some very deep impurities. It means very deep means that the energy level is typically at the middle of the band gap. Okay, in this case, you can actually make a semiconductor almost an insulator, or make it very resistive. And this can be useful as well because sometimes you want a substrate, use a substrate, semiconductor substrate, and then you want this substrate to be completely insulating or semi-insulating, right? Because you don't want any electron conduction from the substrate. And then you just dope this one, right? So one type of example is this gallium arsenide doped with chromium. For example, when gallium arsenide doped with chromium, so basically you can see that this impurity level is almost at the middle of the band gap, all right? So this will make a gallium arsenide semi-insulating, okay? And so of course, for silicon, you can see that so those phosphorus, arsenic, these are called shadow, or antimony, right? These are shadow impurity levels. And then typically for silicon, a donor, we use phosphorus, and then so for acceptor, we use boron. And all these are shallow, dopants. But some other dopants, like and for example, gold, and if you have gold in silicon, this is not very good, all right? Because this is deep level, and then it will increase the resistivity of material, right? And or oxygen, you can create multiple levels. Okay, so those should be avoided. But for chromium, as I mentioned, that if you want to have semi-insulating gallium arsenide, and then you can use chromium. This, actually, it's a product, right? When you buy this kind of wafer, you can specify that I want a semi-insulating gallium arsenide, that basically chromium doped. And so, for example, if you go to the website, and then you can find that people are selling this kind of wafer called semi-insulating gallium arsenide, right? So for many research, you need this kind of wafer. If some of you may have used this one before, so you can see that's semi-insulating, right? And then you look at this resistivity, you can see it's very high, okay? And then if you look at what can make this gallium arsenide semi-insulating, look at this this temperature and this resistivity, and then this is the dopant, right? You can see chromium, iron, nickel, right? Especially chromium. And so if you dope gallium arsenide by chromium, you have very high resistivity, right? So that basically, and then room temperature somewhere here, right? Because this is 1,000 divided by temperature in Kelvin. So this is room temperature basically here, right? So you look at this room temperature and then resistivity of this chromium doped gallium arsenide is very, very high. So basically, it's a semi-insulating, right? Okay, now for the shadow acceptors or shadow donors, it's just called shadow impurity. So for example, we just look at the shadow donors first. If your dopant concentration is not very high, so this means that all these dopant energy levels are separated from each other. So in this case, you have quite a sharp energy level, right? So actually, we mentioned about this one when we talk about the energy bands, right? So we say that you have one isolated atom, and then the energy level of electrons are very sharp, basically just a single energy level. And then you have two atoms come together when they interact with each other, and then they were first split into two energy levels. And then you have more interactions, and then they will split into continuous band, right? So, and then when this, if you have a very high degree of doping, and then of course all these energy levels are very close to each other, and eventually, of course, the electrons from the donor impurity atoms will start to interact with each other to form a continuous band, and that continuous band eventually become overlapping with a conduction band, right? So when this happens, you can see that your EF can be higher than EC, right? So what does this mean? This means that the carrier concentration, electron density can be higher than NC. So this is what we mentioned before, right? So in this case, of course, EF will come above the EC. So when this happens, you can see that you don't need to care about this band gap anymore, because electron already fill up to this level, right? And then above this is empty state, so basically like a metal. So this is the metal, right? Why? Because the electrons are free. You have a lot of free electrons here. Yeah, the Fermi level is already here. So and after that, whatever electron you add to this will be just continue like a continuous band. Just continue to fill up, this continuous band. Of course, when you apply electric field, and then electron will move. Since you have a lot of electrons, and then so you are approaching the metallic regime. So of course, the conductivity will not be as good as a copper, all right, but it's still very conductive. This is called degenerate semiconductor. So is there any usage for this? Yes. For example, sometimes maybe you don't need to don't want to use metal, right, as a conductor, and maybe in terms of process, maybe it's much easier to just use a heavily doped semiconductor as a conductor, right? It's possible, and or in order to avoid any contamination, right? And then you simply use this minus conductor. I mean, depending on your applications, right? But definitely, this degenerate semiconductor is not very useful for making a switch or transistor, because you cannot control, not so easy to control the carrier concentration or conductivity. Okay, so now with this brief introduction of doping, now we try to calculate the carrier concentration in extrinsic semiconductors. This means that in the intrinsic semiconductor, we know how to calculate the carrier concentration. So basically it's Ni. And then, so now if you add impurities, you dop the semiconductors by the impurity atoms. And then we need to look at the carrier concentration again, because now we have two different sources for contribution. So one is intrinsic and the other one is extrinsic, right? So now we try to look at this N-type. So basically semiconductor doped with donors first, right? So again, we have this band diagram. So we have EV, which is the top of a valence band, and EC is the bottom of the conduction band. And for intrinsic semiconductor or pure semiconductor, and then you don't have anything in between EC and the EV, right? There's no available energy states, right? So you only have energy states which the valence band completely fill up at zero temperature, and then so conduction band completely empty at zero temperature, right? So if you add impurity atoms, and then you have this additional discrete energy level, which is called donor energy level, right? And at the zero temperature, and then even though this extra electron is loosely bonded to the nucleus of the impurity atoms, and then this electron cannot escape from this, because at zero temperature, there's no thermal energy for this electron to escape, right? So that's why the dopants or donor impurity atoms remain neutral, right? Because you see have this electron is still bonded to this nucleus, right? And however, and at room temperature, so if this ionization energy, the one we just talked about, is small, and then due to this thermal agitation, and then this electron is able to escape from this nucleus. So this is called ionization, right? Ionization of donor atoms. When this happens, and you create two types of charges. So the first is a so-called this negatively charged, basically electrons. So these are these extra electrons which can move freely in the conduction band. And then same time, you also create this fixed charge, basically fixed to the lattice, right? So these are basically the ions of the impurity atoms due to ionization, right? So after ionization, so this impurity atom become a positive charge. Basically, it's a positive ion, but these ions are fixed to the lattice; they cannot move, right? And then only those electrons which have escaped from this nucleus can move in the material. Okay, so this is called complete ionization of donor atoms at finite temperature. Okay, so now before we proceed further, I need to explain this ED we used. I'm not here anyway, so it's a ED. We just calculate this here, right? So I need to explain this ED first before we move on. So in by convention, we use the same ED for two things. So one is the ionization energy, basically is the impurity ionization energy, which we just talked about. So that basically, in this diagram, is this 45 millielectron volt, right? So this is called ED, called donor ionization energy. It's just energy, right? However, we also call this impurity energy level. So impurity energy level. So when we see this impurity energy level, we are talking about this energy level with respect to the reference for the entire system. So if the reference for the energy we choose is EV, so this means the reference. So EV, it's energy zero at EV. So basically at the top of valence band. If that's the case, and then the impurity energy level we are talking about is this, we use the same symbol ED. So this is ED, this is also ED. But this ED is donor energy level that basically is energy from here to the reference. Okay. So if we use the silicon as an example, so the band gap of silicon at room temperature is 1.12 EV. So if this is a 45 millielectron volt, so this is 1.12, so minus this one. So 1.12 minus this one would be 1.075. So this 1.075 is this one. So this basically is the donor energy level. Okay. And then the same convention also applies to acceptor as well. That's why through in this when we deal with semiconductor statistics, not just this module, okay, and all other people also use the same convention. So once it's in the Fermi-Dirac distribution, and then this basically is a donor energy level, because in Fermi-Dirac distribution, remember we always talk about the energy difference between, for example, EC and then EF, or EV and EF. So now additionally we have an ED, right? The difference between ED and EF, or ED between the middle band gap, or ED between EC and ED, or EA and EV. So all of this, we talk about the energy level, right? So only when we see that it is ionizing energy, and then ED will be 45 millielectron volt instead of this energy level, which is 1.075. Okay, so I hope you can understand this. This is just for the convention, right? Of course, if initially everybody has used a different name for donor ionization energy, and just use ED for donor energy level, and then we don't have this confusion, right? So we have this confusion because that in convention people use both. Okay, use the same symbol for both, but actually, they're different. Okay, so hope you understand this. Now, if you understand this, so now we look at the case that when this donor impurities are partially ionized. This means that at a relatively low temperature, and then not all the donor atoms are completely ionized. So in this case, we can use this Fermi-Dirac statistics to estimate the amount of the percentage of donor atoms which have been ionized, or the percentage of those which still remain neutral, right? So those which remain neutral, just try to realize that when you have a neutral, and donors here. What does this mean? This means that that extra electron actually occupy this energy level, right? So that extra energy electron occupy this energy level. What's the probability for that electron to occupy this energy level? And you simply use the Fermi-Dirac distribution. So that basically this one, right? So this basically is the ionized, neutral donor concentration. And then this is the overall donor concentration, donor atoms, right? So it means that so overall now you have 1, 2, 3, 4, 8, right? So this ND is 8. And then this ND are those which still remain neutral. So that basically 1, 2, 3, 4, right? So that's what you should understand. Of course, in the actual case, we are not talking about 8 and 4, right? We have a large number of ND, and then we just talk about the percentage, okay? So, and then according to Fermi-Dirac distribution, the probability for electron to occupy this energy level simply is 1 divided by 1 plus, something like this one, right? So remember, this ED basically is E in Fermi-Dirac distribution, right? And so now the only extra one here is 1 over GD, and this GD is we just need to consider the this spin degeneracy, because for this single energy level, we can have 2 electrons here with different spin. So that's the reason why we have to take into account this one. That's why I have 1 over GD, right? This is understandable, right? For example, when GD is 2, that means this whole term becomes smaller. So whole term becomes smaller means this will become larger. So why this is the case? Because each level can be occupied by 2. If you don't put the GD here, means that each energy level can only be occupied by 1 electron. That's not right. So that's the reason why I'm going to put this 2 here. And then, so 1 over this denominator is the distribution occupation probability. And then, of course, the number of ionized atoms will be multiplied by this ND, then you get this one, right? So if you don't have this one, this will be F, this is distribution probability, right? So distribution probability multiplied by this total number of donor impurity atoms, then you get a number of atoms which is still remain neutral, which are not ionized with this one. I hope you understand this, right? So in this Fermi-Dirac distribution, so EF is a Fermi level, right? And then ED is not the ionization energy, it's a donor energy level, right? So this means that if your EF is here, say for example, right? And then the ED will be here. Both, of course, have to use the same reference. So if there's a reference, and then EF has to be calculated from here, and then ED also has to be calculated from here, right? That's very important. So if you put the 45 milli electron volt here, but this, you use this as reference, that's totally wrong, right? Because this is a donor energy level instead of the donor ionization energy, right? So I hope we don't make a mistake here. Okay, and then that's the, for donor, sorry. So there's the number of ionized donors, or the electron created by this ionization of the donors, then of course will be given by the total number of donor atoms or donor concentration minus those which have been, which still remain neutral and ionized. So that basically is ND minus this one, right? So, and then of course, this is a fixed charge, is positive, and at the same time, it's also the free electrons which you have created, right? They are the same, okay? And then we just substitute this in here, and then you get this kind of expression. Okay, so I hope you understand this, all right? And so you can do the same thing for the acceptor. So for the acceptor, you can see that now, and you use the same Fermi-Dirac distribution. So basically, you calculate, what are the acceptors which are still neutral, not ionized yet. So basically, to find the occupation probability of holes, right, for at this energy level. So again, we use a Fermi-Dirac distribution, and since it's for holes, so that's why this order. So if you look at the first one, so this is ED minus EF, and then this will be EF minus EA, right? So that'll be different. So EA is acceptor energy level, so that basically is this energy level, right? And then Na is the total number of acceptors. So here we have 8, so that's this 8, and this Na basically is the concentration of neutral acceptors with ionized. So basically this one. Okay. So now we have a Ga here instead of Gd. So Ga is 4 for germanium, silicon, gallium arsenide. So that's because that. So remember here, in addition to the spin degeneracy, we still have a light hole and a heavy hole degeneracy. All right. So that's why eventually this will be 4. Okay. So this will be the 4. So now, otherwise, this is basically the same as Donner's case. And again, we can also try to find out the ionized holes concentration, basically the same as the so-called ionized acceptors. So that basically is the total number of acceptors minus those which are still neutral, right? So substitute this in, and then you got this one, right? Which is the same. Okay. So now, when we talk about this donor ionization, so basically we are talking about this extra one electron here, right? So that extra electron escape from the nucleus, right? And then become freely mobile electrons in the conduction band. So that's called ionization. Then what about holes? So hole ionization does not mean that there's a hole will escape from this acceptor to the valence band. Actually, it's a reverse process. Hole ionization means that this acceptor will grab one electron from the valence band to this, and then when you grab one here, and of course this becomes a negative charge, and then you have create a hole here. That's called acceptor ionization, right? So acceptor ionization means that you grab one electron from valence band, and then donor ionization means that you contribute one electron to the conduction band. So these two are a little bit different, right? I hope you can understand the physical process. Okay. Now we look at the general case that we have both donors and then acceptors docked into a semiconductor, right? So in this case, you can see that you look at what kind of charge we have in this kind of a semiconductor in general. Okay, so first of all, since it's a semiconductor at a finite temperature, and then we should have intrinsic carriers, right? That means that some of the electrons in the valence band will be thermally excited to the conduction band. So this is the intrinsic process we talked in the first half of this lecture, right? So for example, if you have three electrons here initially, and thermally excited to the conduction band, you create 3 electrons here. At the same time, you create 3 holes. So both these electrons and these holes are freely movable, okay, in the semiconductor. These are called intrinsic carriers. Now we have acceptors. So, and for acceptors, sorry, for donors. So we have donors, you know that, so in general case, only part of the donors will be ionized. So for example here, so these 4 donors will be ionized. And then once this ionized, you get the freely movable electrons in the conduction band. At the same time, you also get a fixed positive charge in the lattice. So this field here, right? And then the last one is the acceptors. So when acceptors are partially ionized, so it will create freely movable holes in the valence band, and at the same time, fixed negative charge in the lattice. So that's why eventually you have both positive charge and a negative charge in this semiconductor material. So the negative charge include this one, okay? Freely movable electrons. So basically, you have a intrinsic, extrinsic put together, right? So that this is this one. And then you still have fixed negative charge. So that's due to the ionization of acceptors. So that basically this one, right over here. So since the semiconductor initially is neutral, and then the atoms you dock in are also initially neutral. So this means that overall, this material must remain neutral, right? So this means that the charge neutrality still holds. So in this case, and then this negative charge must be, the number of negative charges must be equal to the number of positive charges. So that's the reason why you have this positive charge have a hole. So that basically have a extrinsic holes and then intrinsic holes. And we don't differentiate the intrinsic and extrinsic holes, right? Because both are movable. And then we have positive charge due to ionization of the donors, right? So this equation we call charge neutrality equation, which is extremely important for carrier statistics in the semiconductor, all right? So now we look at each of these terms first. And so so this we already, calculated, right? So later we just substitute in. So this NP still can be written like this. So remember, when we discuss intrinsic semiconductor, we already derived this kind of equation, right? So at that time, we found out that the EF basically for intrinsic semiconductor, basically this is basically at the middle of the band gap, right? And the same equation, we still can use the same equation and to calculate the electron density, overall electron density in intrinsic semiconductor. Okay, remember for extrinsic. For intrinsic, this basically is Ni, and this is EFI, right? EFI is the middle band gap, and the Ni is intrinsic electron density. for extrinsic semiconductor, so this N includes both Ni and then those due to the ionization of donor impurities, right? So that basically is this one, 2, 2, and then that's this one, right? So that one is given by this. So now the only difference, the EF is not at EFI anymore, right? It's not at the middle band gap anymore. So of course, we need to find out this one. Similarly, for holes, we still use the same equation. So this is the effective density of states in the valence band. And then, so this is EF inside EFI, right? The same thing. And also, we find that this law of mass action also applies to extrinsic semiconductors. Why? And so now by following this, you can see that the N equals NC. This, so I just rewrite this one here. So that basically this one, right? So now what I do that I just to add this one, add the one by this EFI, and then minus another EFI. So that's why I just rewrite this term as these two terms. So you can see that, so since there's a negative sign here, there's a negative sign here, right? So you put here, so this will be positive. This is negative, that eventually, so this term, this term cancels out. It's just mathematics, a mathematical trick, right? So I put here. But now you can see that, what's this? What's this? This basically is Ni, because this NC, this Fi, that's why it's Ni, right? So I just write here. And then this term, I just put here. And similarly for the whole, you can see that I just rewrite this one here, right? And then I separate this one into two terms, this one and this one. You can combine, they're the same, okay? So now this basically is Pi, sorry, Ni, right? So that's this one, right? And the intrinsic carrier concentration. And then this factor is put here, right? So now you multiply this one by this one. So you can see they have Ni squared, right? And then of course, this one minus this one cancels out, because this EF is minus EF, this is minus EFI, this EFI, right? Eventually you can see that there's a law of mass action also applies to extrinsic semiconductor, right? So these few equations are quite important. And of course, during the exam, if it's not an open book, and then all this equation will be given to you, right? So this one, and then, and also, you know, this one and this one. So basically this one, and then this one, okay? So then with this, now we can look at this charge neutrality equation again. So this N, and basically given by this one, right? So this is the one, as we just defined here. And then P is this one. So this is basically this one just defined, right? And then this Na, capital Na minus small na. This basically is the so-called ionized acceptor, and this ionized donor concentration, right? So this field we already derived here, right? So one is this one, right? And then the other one is this one, right? This one. So we just substitute this in. So now we have this this master equation. So now I substitute all these four equations into this charge neutrality equation. So I basically obtain this. This is a master equation for carrier statistics in semiconductor. Okay, so now if you look at this equation, you find that actually this is an equation about Fermi energy, right? Why? Because NC, NC is dependent on temperature and effective mass. So if the temperature is given, effective mass is given, so basically NC is just treated as a constant, right? So that's why, and here, so EC, so if your reference of is chosen at the top of the valence band, and EC is the band gap, right? The temperature is given, this is known. So that's why this whole term on the EF is unknown. And also this one, if the dopant concentration, acceptor concentration is given, and then GA is 4, right? And then the EA is this the donor, so acceptor end network. So if a type of acceptor is known, and this is known, and then this is temperature, again, on the EF, which is unknown. And similarly, you can figure out that, so here on the EF is unknown, the EF is unknown. So eventually, if you can solve this equation to find out EF, so once you find out EF, you substitute here, right? And then you can find out the electron density. And then substitute here, you find the hole density. So this means that so the only thing you need to do eventually is find out EF. So that's the reason why in the first part of this module, I explained that the EF is the single most important parameter which you need to know if you want to understand carrier statistics in semiconductor. So once you know EF, and then you can calculate the carrier concentration, right? And both for both electrons and holes. Okay. So now, if we compare this intrinsic and extrinsic case, there are semiconductors. And I can see that for intrinsic case, this I already shown in the very first second slide of lecture 5, right? So this is the band diagram. So you have valence band and conduction band, right? And so this is a dense of states, and this is Fermi-Dirac distribution. And then, so if you look at so this carrier, free carrier distribution in the conduction band, you have something like this one. And then this is a free hole concentration in the valence band, right? This is due to thermal excitation. I already explained that in the first part. So in between, you have this band gap. So there's no free carriers, right? So basically dense of state 0. And then when you move away, and of course, this dense of state will increase with respect to energy. But the occupation probability, so the distribution probability will decrease eventually to 0. But the product of this one is finite. That's why I have this kind of shape, right? And then to capture total electron density, just integrate from here to infinity. And then total hole density, just integrate from here to minus infinity, right? So eventually you get NP. So that basically for intrinsic case. Now for extrinsic case, for example, now if you dope the semiconductor by donors, so this is a donor energy level, right? It's a very sharp energy level here. So now, of course, in terms of density of states, and in addition to intrinsic density of states, and then you do have another state here, which is due to impurities, which electron actually can occupy this. So once you occupy this, means that the donors are neutral and not ionized, right? If it's ionized, and then so they become unoccupied. So and then this will be, so when this will be so-called this carrier, sorry, and this is Fermi-Dirac distribution, right? So if you look at the movable charge, so this is a fixed charge, it will not move, okay? If you look at movable charge, and then of course the movable charge will only be above this EC, right? Not here. Here you have a fixed, but we're not looking at fixed charge because they cannot move. Okay. And then if you look at this one, so now this one will become like this. Why? Because this will contain both this intrinsic one and then plus the extrinsic contributions. So that's why it will all become larger. But interestingly, you notice that this P intrinsic hole, right? So intrinsic holes, this distribution actually becomes smaller compared to this one, right? You notice. So you add the donors to a semiconductor, you increase the number of free electrons, but at the same time you reduce the number of free holes. So increased number of electrons is understandable, right? Because because donors become ionized, you get additional electrons. Now, what about this reduction in the hole? So this is quite simple here. So just stop here for maybe a while, and then you try to think about this, why this is the case. Okay, so maybe some of you have noticed this, or some of you have not. But anyway, you can think about this one later. So I just give you roughly give you some idea about this. Why there's a reduction of a hole when electron increases. So then you need to go back to look at the mechanism for producing the free holes, right? So you have free holes here because some of the electrons here are excited to this conduction band, right? Due to thermal agitation. Okay. So now, if you have more extrinsic electrons to occupy these energy levels in the conduction band, right? Then it's more difficult for holes to jump into this conduction band. Why? Because these are already occupied by the extrinsic electrons. So basically, you have two ionization process, two sources which contribute to the generation of free electrons to compete with each other. So one is extrinsic. This means that you have to jump from here to here. The other one is extrinsic, and then you only need to jump from here to here, right? So obviously, from here to here is only say 45 milli-electron volt, but from here to here is almost 1 electron volt or more than that, right? So this means that definitely, so this will be easier for electrons from this donor to jump to the conduction band to fill up the lost energy first, right? So once this use up all these lower energy levels, and then after that, so this one will try to jump to other empty states. So other empty states will be, of course, will be farther away from this conduction band edge. So that's the reason why the probability for this will decrease, right? So you can see that it becomes smaller. So I hope you understand this, right? So just like, for example, you go to a classroom, all right, and then these are so-called empty states, right? And then some people just move from the next classroom, and it's very easy for them to occupy the first few rows first, right? Because they come first, right? And after that, and those who are from far away from this classroom will come later. And then since those the front rows are already occupied by students from next room, and then those from other classroom have no choice, and then you have to fill up other one to create this one. Now this will take time, right? You need energy to do that. So that's the reason why, of course, you know, in this classroom example, eventually you may just fill up, right? But in semiconductor process is different. Semiconductor process basically is a dynamic process, right? It's a statistic. This means you jump here to fill up, at the same time you also come back. When you reach your equilibrium, and then you get this distribution, right? So if you, I hope you can understand, you know, this picture. So from here, roughly understand this. So the two sources will compete for the same empty state here, right? So that's the reason why eventually this will decrease. And similarly, you have a similar situation. So this is intrinsic case. And for acceptor, it's the same thing. If you add the acceptor donors, and then so now you have two sources for free holes, for generating free holes. So one is from intrinsic process, and the other one is from extrinsic process, right? So if extrinsic process already creates a lot of holes here, and of course to generate electron here, and then you need to get this electron from other deeper energy levels. So of course the probability will become smaller, right? So eventually you get something like this one, okay? Now, we look at some special cases. So of course this master equation, anyway, I will give you an assignment. So the assignment is basically is for you to solve this master equation numerically, and so that you can calculate the EF, and then you can plot the EF as a function of temperature, and also carrier concentration as a function of temperature, right? So you can solve this numerically. It's not so difficult. So so here we only look at some special case so that we can have some analytical solution. And so the first case is basically the general case, and but we assume that the temperature is high enough, and so that all the impurities are ionized. So both accept donors and acceptors are completely ionized. So we look at this case. Okay. So when this happens, and then of course this is this so-called number of ionized donor, so will be this one, right? Since it's all ionized, that's why basically is equal to the original total donor concentration. And then for acceptor, so remember this contribute a fixed negative charge, right? So since it's completely ionized, so that's why this should be equal to this one, and then you get this one. Okay. So once you have this one, since N, A, and D are given for a certain for a particular sample, and then so N and P we use this law of mass action. So NP equals Ni squared, right? So that's why you can either replace P by N or replace N by P. and eventually you can solve both equations, right? The solution should be the same, and then you find out n basically came by this one, and the p is given by this, right? So, and again, of course, when this ND, for example, if is dominantly n-type, the ND is much larger than NA, just ignore this one. And then further, if ND is much larger than NI, you ignore this one. That's why this whole square root will become ND divided by 2, right? And then, of course, this will be another ND divided by 2. Eventually, n basically is ND. That makes sense, right? So this means that if it's a dominantly n-type, this means that you have a large donor concentration, and all the donors are completely ionized. And then this donor concentration is much higher than the intrinsic carrier concentration. And then eventually, the electron density you have here, so basically it's n, right? And then what's p? So p basically is ni squared divided by n, right? So that would be p. Okay, that's how I can find out this. And now we look at different temperature region. So so suppose we have an n-type semiconductor, means that we don't have any acceptable impurities, means that Na is 0. So when Na is 0, and then at a low temperature, so it means that this thermal energy is smaller than ionization energy, right? So when this happens, of course, only part of the donors will become ionized, okay? And then we also assume that this ND is much, much larger than P, because Ni squared divided by N is P. That means the dopant concentration is larger than intrinsic hole concentration. So this is understandable because at low temperature, you don't have so much intrinsic free holes or free electrons, right? So now we come back to this master equation. Since Na is 0, so this equation is basically a master equation, which is a copy here, right? So this one we copy over. So that basically is this one. So when this Na is 0, and then so that because we assume that there's no acceptor atoms, okay? So that's why this will be 0. And then so this one can be ignored. That's because that EF, so it is n-type, so EF basically will be somewhere here, and then so EV is here. So that's why this is almost equivalent to a band gap. And then your KPT is very small, low temperature. So that's why eventually this is a huge number. So this is a huge number, there's a negative sign here. So that's why I just ignore this one, right? So this term is very, very small. And then after you only have this one and then this one, right? So for this, so we just write here, and then so this, I will just write here, okay? So now we look at this one, compare this one with this. Since ED minus EF, if this KPT is very small, the KPT is very small, and then if it's ED minus EF, basically this one minus this one, right? So ED minus EF is a negative. And then there's a negative sign here, so that's why eventually this is positive. So if this is much larger than KPT, and then so we can ignore this 1 because this exponential time will be much, much larger than 1, right? So that's a low temperature case. And then we ignore this one, right? And then we get the ND divided by GD, and then this will flip over, right? Flip over because this is at denominator, so now put that in the numerator. So you just remove this negative sign. Remove this negative sign, come here, okay? So this one just right here. So now we just redo something about this one. It's very easy. We just solve this because there's the one negative sign here and it's here. So you have a positive EF here, and then this is negative EF. So you just bring this EF to the left-hand side, and then whatever other to the right-hand side, and then you take a logo, right? After that, you bring KBT over, so you'll get this one. All right, so from here to here, very easy, so you can do it by yourself. So now, if you look at this, actually is very interesting. So what happens here that, of course, once you have this one, you substitute this in here, and then you get N. So this is N. This actually is electron density, right? So again, this is not so difficult, right? It's just a algebraic operation. So you can do that. You can find out N, which is given by this one. Okay. So now, so once you get this, look at this. This is actually very interesting. You see what happens here that so EC plus ED divided by 2. Remember, ED is the donor energy level. So this one. So EC plus ED divided by 2 basically is the middle between this one and this one. Okay, and then plus this one. So again, this can be a very small number because ND and NC, this is GD, right? So NC and ND almost equal to if these are ND typically will be much smaller than NC anyway. Okay, So that's why this will be a very small number. And so you take a log, it becomes even smaller. That's why I just ignore this one. And then eventually your EF is somehow at the middle, right? That's what you see, okay, here. And this, and then look at the carrier concentration, and then given by this. This actually looks very much like an intrinsic semiconductor case. So for intrinsic semiconductor, remember this Ni is given by this one, Nc and V product to power 1/2. So look at this one, Nc and D. Nc is the same, but Nd is different from Nv. So Nv, remember, is the effective tensile states in the valence band. But here, Nd is this dopant concentration, right? And then Gd basically is 2 is due to degeneracy, right? So that's why you don't have this one here. So 1/2, the 1/2 here. And then exponential, so exponential. So minus sign here. So 2 kpt, so 2 kpt. So the only difference here, so this Eg is Ec minus Ev, is Ec minus Ev. And then this one here, Ec minus Ed, is this one minus this one, right? And then you look at the Fermi level. So this one, Fermi level, so remember, right, is at the middle of this band gap. And then this Fermi level is the middle between this one and this one. It's just like you have another intrinsic semiconductor, right? Of course, not exactly the same, with a band gap which is much smaller than this original band gap, right? And then this will generate free carrier much easier. So this means one way to understand this is just like you have two semiconductors. So one with a large band gap, okay? So that's your host semiconductor. The other one is some sort of another semiconductor embedded in this large band gap semiconductor, but with a much smaller band gap. And that band gap is basically determined by this ionization energy. Since this gap is much smaller than original host energy band gap, as a band gap of the host material, that's why at the same temperature, it's very easy to create free carrier from this narrow band gap semiconductor than from this wide band gap semiconductor, right? Of course, this is not another semiconductor. We only have one type of semiconductor, for example, silicon to silicon. This is mathematically, you can understand this way. But physically, of course, we don't have two semiconductors coexist in the same physical space, right? So this is what you can understand. But there's a critical difference. So what's the critical difference? The difference that for the original intrinsic semiconductor, the host material, when you get one free electron here, you'll get another free hole here. But for this dopant, you only get a free electron. You don't get a free hole because the positive charge left over are fixed. They cannot move. But for intrinsic semiconductor, the holes can move. So this is extremely interesting. Why? Because when you use this mechanism, extrinsic mechanism, which is generate free carriers, you only generate free carrier of one type, right? So basically, if the dopant is a donor, and then you get N type, and then dopant is an acceptor, you get P type. But intrinsic, you can only get intrinsic type. This means that it's neither N type nor P type, right? So this means that this extrinsic, this doping technique is not just to create more free carriers in a much easier way. It also can control the conductivity type, which is extremely important for semiconductor. You cannot do this for metal, right? So that's the reason why we can have transistors, all these fantastic devices, okay? So that's extremely important. And I hope you can understand why semiconductor is so important, right? Which you cannot get the same type of property in a metal, right? Now, similarly, and if you look at P-type semiconductor, and so your donor concentration is 0, and but temperature is also quite low, right? In this case, I will not repeat this anyway, so this will be 0. This can be ignored because this is very small, all right? And then this ND, the ND is 0, that's why you only have this term and this term. So similarly, you just rearrange the two equations and solve it, then you get EF. So now this EF, you can see that it's EV plus EA divided by 2. So EV is here, and then EA is here. So divided by 2 basically is the middle between this one and this one, right? And then plus a very small number. And then look at the whole concentration and compare it with the intrinsic whole concentration. So NV, and then NC as NC. So now NC is your NA divided by GA. So that basically this one, right? And then this is 2 kBT at 2 kBT minus sign. So minus sign. So your EG now is EA minus EV. So that's this energy level minus this level. Basically, is this gap, right? So again, looks like you have another intrinsic semiconductor with a much smaller band gap, which is embedded in this large band gap semiconductor, right? And then, so this small band gap semiconductor only create free holes, but this large band gap semiconductor create both holes and the electrons, right? So that's a difference. And then at the same temperature, it's much easier to create free holes from this impurity energy levels because this gap is very small, right? So that's a bit similar to the N-type, but now you create holes. That's the only difference. Okay. So next, we come back to this N-type again, but we look at the case that this temperature is increased, right? Now we come to intermediate temperature range. So in this range, so all the donors are completely ionized, right? So in this case, of course, and so we come to this very simple situation. And so I already explained it, right? Because and this ND typically is much larger than NI, and of course NA is 0. So that's why I just ignore NA. Since ND is much larger than NI, so eventually, so this square root will give you ND over 2, another ND over 2, you eventually get ND, right? So this means that in this intermediate temperature range, so you have a lot of free electrons. The electron concentration is the same as the dopant concentration of donor atoms, right? And then of course, so this is equals to N. So N is given by this. Still remember this equation, right? This. And then from here, you can find out EF. So EF is given by EC minus KBT, and then this one. So again, this is can be a quite a small number, and depending on depending on ratio between NC and D. But anyway, so when this happens, and you can see EF will be somewhere here, right? So why EF now is below this donor energy level? Because we assume that in this temperature range, so all these donors are already ionized. Ionized means that electron will not occupy this. So electron will not occupy this means the EF must be below this, right? So that's why your EF will be here. So so this is a minus means that if you increase ND, you increase ND, and so NC becomes ND become larger. This means that this becomes smaller, and then this EF will move up. Okay, and then if you reduce ND, increase ND, and so that will move up, right? So if you reduce ND, and then this will move down, right? So that's what you will see. Okay, and similarly for the same temperature range, and then we can have this P-type. So P-type is ND 0, right? And then so the whole basically concentration is almost same as this NA. Okay, so and then so now you can see that use this one, you can try to find out what's the EF, and then you find out the EF is basically is above this level. Okay, so that's what you will see, right? And this is similar to N-type, but the only different now is this is the P-type. Yeah. And so once you know P, and of course you can calculate the N. So N basically is Ni squared divided by P, right? Then you get everything. So next we look at the high temperature range. So now I come over here about room temperature. At high temperature range, what happens that there's all the donors, of course, are already ionized. And if it's for P-type, of course, all the Na are ionized. But compared to the intermediate temperature range, so what's the difference? That now you have a large number of intrinsic carriers. So this means that the total carrier you have, you cannot ignore this intrinsic carrier anymore. So you have N
which is ND, so because completely ionized, and then plus this Ni, right? So this is Ni. And then for p-type, and then you have all acceptor ionized, and then plus is Ni is due to this intrinsic carriers, right? So that basically you can see that they are more. So these are due to whatever for this case. So these are due to intrinsic carrier, and these are due to sorry, these are due to extrinsic. So these are due to intrinsic. So intrinsic can be comparable to an even larger than this extrinsic carrier concentration, depending on the temperature, right? Okay, so now if we summarize together, this is a very important chart, and then so roughly you can understand these three different regions. So what's plotted here is this is a reciprocal temperature, right? So it's T to the power -1, and of course I don't have any scale here. If you want, you can always put 1,000 divided by T. But since I don't have any scale here, it's just arbitrary. That's why it's just T to the power -1. Okay, and then so this is the formula work. That's a band diagram. So the band diagram is superimposed with the formula work. So this is formula work. And so this is EV, right? And then this is EC. And then so if I focus on N type, so this will be ED, right? So you should have the same one for the P type. Okay. And then so this is log N, and of course you should have a log P as well, right? So we look at this is three different temperature regions. And so first, at a very low temperature, so that basically right here, right? The very low temperature, we already found out that so this formula work is somehow in the middle of EC and then this ED, right? We already calculated it, so that is this one, right? So EC plus divided by 2 plus this one. So it's just you can find this one from previous slides. We already have this one, right? So it can is constant, okay? And then when you come to intermediate temperature range, so intermediate temperature range, so EF is given by this, EC minus this, right? So when temperature increases, and then so this term becomes larger, so eventually it will just go down like this. And then when you reach the intrinsic region, so this is intrinsic, very high temperature, right? Because it's 1 over T, so this is very high temperature. So when you come to very high temperature, and then intrinsic carrier, then concentration is larger than dopant concentration. And then, of course, the EF will be mainly determined by intrinsic carrier. That's why EF will approach the middle of band gap, right? So that's what you see. Okay. And so if you look at the electron density, so within this range, and so this is electron density we found out, right? If you forgot about this, you just go back and check the previous slides. And then, so this one, if we use a log scale, we take a log of this one, and then we plot this one as a function of 1 over T, and then you get a slope. So the slope basically is given by this EC minus ED divided by 2KB. Of course, it's negative, right? That's why you get a straight line here, right? And then the gradient. So this gradient, so you can see that this gradient roughly is given by ED over 2K. So this ED, of course, so here ED is the dopant energy level. So here ET, you know that is ionization energy, right? Because EC minus ED is ionization energy. So that's why the gradient basically is ED divided by 2K. So basically this one, okay? And then after that, when you reach the intermediate region, and then N roughly equals ND, it does not change. That's why you get this, right? So it's a constant. And then you come to intrinsic region. So this intrinsic region, so this term will become dominant and much larger than this one. That's why you ignore this. And then you take a log, of course, this slope will be minus EB over 2KB. That's why this is EG, sorry, EG. EG over 2K, that'll be this one. So this gradient, which is negative, right? So in the assignment, I hope you can calculate all this by yourself by solving the mass equation numerically. And so, but this is by approximation, right? So our approximation, that's why you see this, sharp turning point, right? But if you use a numerical calculation, and you'll find that actually you get a gradual change, right, of carrier, gradual change of carrier concentration and also from level, right? So then you find out. And then since you use a numerical solution in addition to n, right, and you can also calculate p. So for this, for n type, of course, dominantly electron conduction dominant, but they say p is not zero, right? It means the whole concentration is not zero, and then you can calculate by yourself. That's why in the assignment you're supposed to calculate both this Fermi energy distribution, Fermi level as a function of 1 over t, and log n as a function of 1 over t, and also log p as a function of 1 over t. Okay, so this is what we do. So this chart is very important. So I hope I already put all this color code here for you. So green means low temperature, and the blue means intermediate temperature, and then this red, yellow means high temperature. And so the temperature scale roughly is given here. So please try to spend some time to look at this chart. And then if you don't understand this, you go back to previous slides, right? So if you can understand this and also the master equation, so in principle, you should be able to understand the characteristics in the semiconductor. So of course, we can also try to vary, to plot this chart in different way. And for example, if you vary ND, this basically dopant or ND dopant concentration, and this is donor concentration, and then acceptor concentration, and then if you fix temperature, then you see that this formula will change like this, right? So this N type, right? So initially, and so when ND is high, so this formula is close to EC. When you reduce ND, and then gradually you go to intrinsic case. So when you reach the pure intrinsic case, so the formula will approach this one, right? And then for P-type, so initially the formula is near to the valence band edge, and then you reduce this acceptor concentration, and the formula will move back to the middle of the band gap. Okay, and this chart is you plot EF, so reference is the middle of the band gap. Basically, is EFI. All right, and then you look at this, and then this is a temperature. It's not the reverse temperature, it's simply temperature, it's just temperature. And then you can see that when you increase temperature for different dopant concentration, of course, the formula will vary differently. For very low dopant concentration, this is the intrinsic case, right? And then when you increase temperature, and then you will reach the intrinsic formula. Sorry, that's not this is the formula, or let me see. So when temperature is very low, and when the temperature is very low, so this is intrinsic level. The EF minus EFI. Yeah, you're right. Okay, you're right. So this means that so of course, when you don't have any dopant, so this means that when you change the temperature, and then the formula will not change. But at 10 to the power 12, and so even at this dopant level, so you can see that this formula will change with respect to temperature, right? So, and of course, if your dopant concentration is very high, then the formula will change slowly with respect to temperature. If it's very low, then you can see that it will change very fast. Anyway, you can try to plot this one by yourself. Okay. So, and then one example here. This actually is one of the previous year's exam question. So, if we assume that we have a silicon sample doped with arsenic at a concentration of 10 to the power 16, right? The ionization energy of arsenic is approximately 54 milli-electron volt. And then at the 300 Kelvin, the intrinsic carrier concentration of silicon is given by this. It's quite low, okay? And the band gap is 1.12 electron volt. So the question asks you to make reasonable assumptions and then answer the following questions. So first, the question asks you to compute the electron concentration in the conduction band. So remember, so the question asks you to make reasonable assumptions, right? So in this case, since room temperature, and then this is considered low, shallow impurities. So this means that we can assume that so all these impurity atoms are completely ionized. So this means that since this is arsenic will give you N-type,
this means you get a free electron is roughly of this concentration. And then since this is much, much larger than the intrinsic carrier concentration, so that's why you have two sources for free electrons. So one is from this one and the other from this one. Since this one is much smaller than this one, so you just ignore this. And then, so this basically is the electron density. So something like this one. This is the like in the intermediate temperature range we just talked about, right? Is eventually given by this ND. Okay. Second, compute the Fermi level and indicate it in the energy diagram. So Fermi level, we can use that equation because we know that N is equal to Ni, and then another exponential factor, which you have EF minus EFI. So EFI is the middle of band gap, right? Since we know Ni, we know N, so we can calculate from here. So we know N, know Ni. So just use this formula, right? This is given in one of the slides anyway. So, and then we just calculate this one, then bring this one over, and then take a log from both sides, and then you can get this one. Since N has 10 to the power 16, Ni, we have number, substitute in, and you find this is 0.368. Okay, so this is from middle of the band gap, this EFI. So since band gap is 1.12, so 1.12 divided by 2 is this one, right? And then you 0.368, and so just calculate from here, so roughly here. Okay. So next one, and compute the fraction of dopant that are ionized and compare it with the assumption and made in part 1. So in part 1, we assume that it's completely ionized. But even at this room temperature, it's not 100% ionized, right? So we have the formula to calculate the fraction of this dopant which ionized. So the ratio is given by this one, right? Use the formula version. So and the EF minus ED, and so EF is here, all right? And then ED is 54 milli electron volt from the conduction band, right? So that's why I can calculate what's the ED here. And then you can find the EF minus ED, basically this one. And substitute here, and then GD is 2, right? And then find this is 99%. So this means that the assumption that it's complete ionized is reasonable, right? Because 99% already ionized. Okay. And compute the whole concentration in the valence band and compare it with the assumption made in part 1. Okay, so the whole concentration, since we know NP, which is always equal to Ni squared, so that's why the whole will be thinking about this one. So this means that part 1 we assume that we only have electrons, and the whole can be ignored, so which is right. Yeah, the whole concentration is much, much lower than that of electron concentration. Okay, I think that's all about lecture 5. And then, so in lecture 5, so basically know that, so now we know how to calculate the carrier concentration in all different temperature range. So once we know the dopant concentration, of course, we need to know what kind of semiconductor we have. So basically silicon, germanium, or gallium arsenide, or other type of semiconductors. So once we know the carrier concentration, and so basically we know movable electrons and movable holes, and then next week, and we are ready to discuss electric conduction. So this means that electric conduction, for electric conduction, what you need, not just the free carriers, and also you need to know how fast the carriers can move. And then so that when you apply a certain driving force, so basically electric field, and then you can calculate the electric current density, right? This is what we'll do next week. So we'll just stop here for lecture 5.